Yeah, thank you very much. Good morning. Like the chairwoman said, I will present a paper about prediction of size effect and fatigue limiting stress in LPBF maraging tool steel. So the plan of the presentation is say a few words. Yeah, closer? Yeah, okay, sure. The plan of the presentation is to say a few words about the motivation and the aim of the study, then about the materials and specimen fabrication, testing, then about the model, obviously, and showing the results and summary. So the motivation is to better understand how the size effect and scatter influence the fatigue performance on often LPBF manufactured tool steel, where defects are geometry, scaling components, and complicated of the definition of the reliable limit stress. And the study aims to establish a probabilistic framework for this type of steel by developing a reference Weibull-based distribution of normalized fatigue lives that reveals the stress limiting asymptote and enables rescaling of the different specimen sizes and elements later. So the material that was used for a study is the EOS maraging steel MS1 powder from EOS, but it's 18Ni300 maraging steel. We use the EOS M280 printer to print it with a laser bed fusion and nitrogen atmosphere. The chemical components and the information about the powder are also on the slide, but I will not be reading them. So this is the system and the building condition, the laser power, the scanning speeds, hatches, and all the other important stuff. After the printing, the elements, the specimens were heat treated with 490 degrees for 4 hours and a slow furnace cooling. This is according to the EOS data sheet, right? It's what the producer tells us to do. What we did in an extensive test for the fatigue properties, different heat treatments, and honestly, that the best one were the EOS told us, so we stayed with them. So it's for 90 degrees. As a start, we did some tensile tests, 3 specimens in this case, on the hydraulic machine from Instron, and you can see the results on the slide here. The yield strength changes from 1,940 to 983 megapascals, so the results were quite close, and you can see that the material is, let's say, elastic brittle at least. I mean, it's not really elastoplastic. The elastic part is very high, much higher than 1,500 megapascals, and the test will be carried out way below, which I will show in a moment. So after the initial tensile test, we did some fatigue tests. They were all uniaxial tension compression with constant sinusoidal amplitude of load ratio -1 or -1 in room temperature. And there was also a failure criterion. It was either a complete rupture or 50% for force drop or displacement amplitude drop in this case. So we did 2 testing campaigns. The first one was a, let's say, calibrating campaign. It was 80 specimens on 4 different stress amplitudes from 550 to 1,200 megapascals, 20 specimens each level, just to get a calibrating curve for the model. And then we did a verifying campaign with a different specimen size. I mean, the shape was close enough, but it was a little bit bigger, the specimen. It will be shown later. And also some of the specimens were run out, and we decided that the run out will be 1.2 times 10 to the 5th, so 120,000 cycles. So just a short reminder about the SN curves and the model we are going to use. We have low cycle fatigue, high cycle fatigue, and very high cycle fatigue, and The tests we did were all in the regime of elastic stresses, so we did high cycle fatigue in this case, but the model is a class 2 model, so it can be applied to the very high cycle fatigue, not so much to low cycle fatigue. But yeah, high cycle fatigue and a very high cycle fatigue is what we can use the model for. So the specimen dimensions are on the slides. You can see that the main difference was the dimensions in the middle here. So diameter of 2.96 was the calibration one. The bigger one were 4 millimeters. The machine we used was an electrical machine with only 10 kilonewtons on force. So we did use some small specimens, but it was it's standard when you talk about the scaling. So this is the results of the calibrating campaign. Like I said, 4 different levels of stresses and 20 specimens each. 2 of the lowest one were runouts, but only 2 of them. And about the model and about the mathematics behind it. So we use the variable distribution, which I think fits well to the topic we are dealing with. So fatigue life is basically a probabilistic model with a bit of scatter, right? And the weakest link approach is, I think, quite well suited for 3D printed specimens. So this is why we use the variable model, but we also use the Castillo et al. Normalization model method to normalize the fatigue lives to a stress-independent standard variable that can be later scaled, but it's not related to the model. Doesn't take into account the size, but we do have a scaling factor here, the omega. This is the variable distribution, but with normalized variable. Also with the omega here that basically scales the model to a different volume of specimen in this case. Then we could get the asymptote for the model, and just to show it on the slide, there's a minimization function that will be talked about a little bit later. So to make it more clear, here's the graph model of the graph version of the model. So we have a scattered standard fatigue test. We use the minimization and get the asymptote for the standard, let's say, experimental results. Then we normalize them. We use the maximum likelihood estimation for the normalized specimens. So we get new asymptotes for the normalized version, and then we can get the distribution parameters. So basically, we normalize the results and get the size-independent fatigue life model that can take into account the size effect of the specimen. This is just a reminder how the variable curves looks like. Those are the asymptotes for the hyperbolic SN curves, let's say, in this case, with different percentiles. The higher the certainty, the closer we get to the asymptotes, but we obviously should never go past them, and all the percentiles share the same asymptotes. That's why when you get the asymptotes, you can calculate all the different percentiles. So this is just a plot of normalized data on a variable distribution, just to show it was, let's say, fitted correctly. And getting to the results with this Castillo normalization model curve, those are the calibration results, those 80 specimens here. This is the red line is a median of the model, and percentile is, in this case, 5 up and 5 down are the dotted lines. So this was the calibration, so obviously it fits with 98.7 significance level, and the test results that we use to check the model has a slightly lower significance level of 94 almost %, but you can see the results here on the same lines, let's say, and this is like the representation of the different SN curves, where the red one, the orange one, I think, is for the calibration. So in this case, the omega value So the volume is 1, because on the here you can see the equation for the omega. So it's basically a current volume divided by the calibration specimen volume. So in this case, it's just 1. This is the middle dashed line is the test results we use. So the omega here was 1.461, so 46% bigger volume of the specimen, and as predicted, as we should predict, the fatigue life was a bit lower, and this is just a representation of what would be if this omega would be 2 times, the volume would be 2 times bigger. We didn't do any tests. It just shows that you can easily change the model and get somewhat reliable results. But we only did checked it for the two lines, like on the topper line. So, and going to the summary, so the fatigue test conducted on specimens of varying sizes have confirmed a distinct size effect, where smaller specimens exhibit higher fatigue strength for a given probability. Under the tested loading condition, the volume of material holding the normal stress distribution demonstrated the ability to define a model predicting the influence of the size effect on the fatigue life. The scale parameter identified from the extensive statistical data set can be rescaled to incorporate the size effect for this. We tested it for this steel, so we can say only it worked for this steel at this moment, enabling more accurate predictions for different sizes and shapes maybe. Applying the probabilistic model of Castillo et al. Demonstrates that normalizing the governing random variable provides a robust framework for predicting the fatigue limiting stress using test results from various high cycle fatigue stress levels. And thank you very much.